Hey, what's going on, folks? It's Mike here, and welcome back to my deprogramming language series. In today's episode, we're going to be taking a look at operator overloading in the deprogramming language. We'll go ahead and show you how, and then we'll talk about the why you might want to use this feature throughout, so you can see for yourself. So anyways, let's go ahead and dive onto dlang.org, our favorite deprogramming language website. And what we're going to go ahead and do is open up the language reference here. And also in the documentation, I'm going to right-click on articles because there is some rationale for why things are designed as they are. And again, operator overloading in the deprogramming language itself is pretty clean. And again, it fixes up some of the issues with other programming languages as far as where, for instance, you're allowed to do the operator overloading, why it's designed with templates, and so on. So anyways, we might dive into that, but we're going to do a lot of live coding today and also bring in some of the other things that we've talked about in various deprogramming language lessons. So again, head over to courses.msha.io if you haven't, and if you haven't seen some of the lessons like functions, working with unions and structs, you're going to want to check out this series and or this YouTube playlist and just kind of track your progress. Make sure you knock out a few videos before doing this one. It's a little bit more advanced if you're just diving into the deprogramming language series. But anyways, let's go ahead and dive into it. So anyways, let's go to operator overloading here. And this is going to be kind of an example-driven lesson here. We're just going to want to try some stuff out here. And basically the idea is that if we have some custom type here, and we want to be able to use operations like minus, plus, 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 minus equals, the little tilde for concatenating things, plus equals, the shift operators, slicing, $, you name it. All of these symbols are, well, they're just functions. So what we're doing when we're operator overloading is when you see something like a minus sign, for instance, D is just rewriting as op unary here, whatever the argument is, and then, of course, performing the operation here. Okay, so let's go ahead and create a little type here, and then we'll look at a few examples here just so you can get comfortable with the idea of operator overloading. So what I'm going to go ahead and do here, let's move our window to the side, and I'm going to create a type here. I'm going to create it as a struct, a vec2 here, just to make our, as a simple example here, and let's have a x and a y field here. And again, this is representing or could represent something like a point in space. It's supposed to really represent sort of a magnitude and direction from the origin. But, for all we care, it's just a custom type that isn't built into the D language. I've made it a struct, which there are some differences between structs and classes when you're doing operator overloading. So again, if this is your first video, you're going to want to go and make sure you're familiar with things like reference types, which are classes, and value types, which are structs. From some of my previous videos, because that's going to have some repercussions if you want to overload assign, for instance, or do a comparison between two different types, what that actually means. So anyways, you'll find some differences with how classes and structs are handled. Again, it's not to make anything complicated, you just have to think about it. But anyways, we have this type here, struct, and ultimately what I want to do here is something like, let's just create as an example a vec2 v1, and I'm just going to assign, well, we can, because I'm not going to define any constructors here, I could just give it 5 and 6. And again, if you haven't seen why, you'll want to look up struct literals in my playlist here, and let's just create v2, which is going to be 1 and 2 here. Okay. And again, if we want, we can write out using right line here, v1, and we could give a little printout here, v1, and let's go ahead and write out v2, and let's just go ahead and make sure our code is working here. Oops, already I've messed it up here. Let's see what I did. The classic. Sometimes my C++ brain messes things up here. But let's see here. Let's assign this to vec2, and assign this to vec2 here. There you go. I got to go rewatch my own videos. So there we go here. Okay, so simple enough. We've got our custom type. We could, use this in some context here. But ultimately, what we're going to want to do here is something like this, where we want to create a vec2 that holds a result, and do something like result equals v1 plus v2. Okay. And if I try to run this, again, you're going to get some message saying incompatible types v1 plus v2. Both operands are of type vec2. I mean, we don't know how to handle this plus operator here. And again, I'm actually going to call it plus operator, but this plus function. Again, we want to think about these as functions, because what D is really doing is taking this binary operation, meaning of or relating to two things, which again, let's bring in the definition here, binary, relating to or composed of two things here, and trying to return a result here. Okay, so let's actually look at, and again, we're just going to search these op binary. As a helpful tip, you can just put the little parentheses here, and it'll probably bring you to some code here. But we have op binary here, and basically, just to let's take it from the top here. So the following are binary operations. Plus, I want to add two things together. I want to subtract two things, multiply two things, divide, etc., etc. So A op B, anytime I have this form. There's also op binary. I'm just going to mention it briefly here, right, which reverses the operation. So if you want to do B op A, okay, so it's kind of nice. I mean, I think that's a really nice thing in the language that you can reverse or have control over this. So again, D gets a lot of the operator overloading stuff right, in my opinion. So anyways, this is the form here. These are the overloadable things that we can do here. So if you want to build a data structure that says is A in B, or if A in data structure B, you can do that. So that's pretty cool. So anyways, how this works is most of the operator overloads are template functions. So you're going to have this template here. And then, of course, whatever the right-hand side is. And then you can do your operation here. Okay, so a few things just to set us up here. Right, we can run this code here and see that it breaks here. And since we're going to be testing a lot of things to see if they actually work and what the values are, this is a great candidate to remind you, and again, you'll have to look at my unit testing video, that usually, we don't really need a main here. We're going to want to build little unit tests. Okay, so again, try to build this. It's going to complain about not having a main here, so you can add a main, but we actually want to add unit test as well here. Okay. Now, if I do these in the wrong order, like I did here, so let's add our main and then compile our file, then we'll get to back where we were. Okay. So each of these are going to be little unit tests as I add different versions of the overloads here. So again, you can see how it compiles here. Okay. So this is just going to be our basic binary op binary test here. And what I'm going to do here is, again, op binary. As a template, we take in some operation. And then what is to the right-hand side, the thing that I'm performing on. Okay, so that's going to be some other vector, some vec2, and I'll just call this B, for instance. And that's the idea. And then, of course, the return type, well, let's just look at the form here. I'm returning a vec2, the result here. Okay, vec2. Now, whether or not I want to return or modify v1, I don't want to do this. So you could do there's a few things you could do for the return type. Let's leave it as a vec2 here. I probably don't want to return this object, okay? Because again, this is going to be an operation, one thing plus another, for example, and retrieve a new result. So again, there might be optimization options that you could think about, but again, I want to store a result. So most of my operations are going to look like this, where I return a result here. Okay, so let's just start with that. Let's compile this and see if it does something. Now it at least compiles. Okay, and again, just to make this interesting, let's write out our result. Now this is going to give us a nonsense result, right? This is going to give us whatever is here. We haven't done any operation. And again, remember, what's the default type for a float? It is a nan value, okay, not a number here. So again, look at my basic types if that's video, if that's new. But anyways, that's the idea here. Okay, so that's op binary, but now let's actually implement it. Okay, so what do I want to do here? Well, I want my result x to be equal to this dot x plus b dot x, okay, or the right-hand side. Again, if we're coming from C++, that's how I usually do things here. In C++ operator overloading, but we're in D, we're going to do things properly here, don't worry. So anyways, that's our result here, right? We're going to write out to our result, well, whatever our current object is, and then the right-hand side x here, okay? Compile, run it, and that works perfectly. 5 plus 1 gives us 6. 6 plus 2 gives us 8 here. Okay, so simple enough here. Okay, great. And again, what this is doing here is rewriting this as result equals v1.opBinary plus here v2. Okay, so again, the decompiler is rewriting plus, which again, it's not anything magic. It's just a symbol that represents a function name. Okay, great. Okay, let's play around with this a little bit more in this unit test. Let's create another result here. So let's create another unit test just to make this kind of nice. And I'm going to split these windows here just so we can have our tests and our actual code perhaps as the way to do this. But what I want to do here is let's copy this result here. And let's shrink this down just a little bit. So there we go. Use your vim foo here. There we go, just because we want to see more code. So anyways, what I'm working with down here is, let's do minus now. Okay, v1 minus v2. So we run this. Oh, well, we got to define v1 and v2. Sorry, we're going to have to do this for every test here. That's okay. Something like that. We'll just do a lot of copying and pasting. All right, anyways, there's our unit test. Perfect. Let's run this. Now, wait a second here. So here's my, first little test that I did here. And maybe let's get rid of our right line result here. All right, we don't. Let's get rid of, let's do a little right line here. Let's just put a little space in between them. Okay, so I'll do that for all of my tests. But what happened here? What do folks notice that's wrong as I, format this text? Yeah, we get the same result as addition here, but, I'm doing subtraction. So the obvious thing here, if I look at my op binary, is, right, I'm always doing plus here. Okay, so that's where this op comes in here. Okay, so what can I do here? What if I put in like op here? Does that do anything? Nope. Okay, so again, this is a string, so we got to do something with that. But this is where, we get a few options here. So because it's a string, I can do one of two things here. I can say something like if, and because this is a template argument, well, let's do static if. Okay, so op, if I detect at compile time, because again, this is what's happening at compile time, right? I'm taking a template, generating a version of this function here. Well, I can have the plus version and the minus version here. Okay, so let's go ahead and do the minus version, and let's do minus and minus, and voila, that's looking better to me here. So 5 minus 1 will give me a result of 4. 6 minus 2 will give me a result of 4. And then my addition, 5 plus 1 gives me 6. 6 plus 2 gives me 8. So it's working. Great. So no problems there. Okay, let's go ahead and create another unit test here. Minus is working perfectly fine. Let's go ahead and do multiplication. Okay. And let's go ahead and multiply for our next test here. And oops, I have plus, I have minus, I don't have multiplication. Okay. So let's try to improve this code, and then we're going to revisit this idea of what it means to multiply two vectors, for instance. We can use something known as a string mix-in here. So that's even better. Or let's get rid of this here. And instead of repeating our code, let's say if op is equal to minus or plus, well, now we can actually use these, again, compile time features, because these are templates, to say, let's just do a mix-in here. Let's write this as a string. And the whole thing, don't forget to include the semicolon, because again, all the string mix-in is doing is translating the code here. But instead of writing out plus here, because it's just a string here, let's just concatenate it inside here. Okay, I'm going to do the same thing for the y value here. Carefully making sure to put in y, and there we go. Okay, so let's go ahead and write this out. Now my code compiles here. Okay, I haven't handled multiplication, but I can now. Okay, so if I want to add in op equals times here, I can do that. Okay, now it's doing, okay, whatever it means for 5 times 1 to be 5 and 6 times 2 equals 12 here. It's handling that. And I didn't have to write any other code. I'm just handling all the operations. Okay, so here's where we have to think just a little bit, though. Multiplying two vectors, we need to think about, like, maybe that represents, maybe we're trying to do like some cross product thing. So, in that case, that's where I would come down here and have the, static if, because we have some different logic for multiplication, right? Maybe this means, something else, okay, for whatever your data type is. I'm going to restrict things just a little bit here. And let's just go ahead and refactor this code a little bit, and then we'll handle scalar multiplication properly. Okay, what it means to multiply. Okay, so what do I mean by this? First, refactoring. I don't necessarily even need to do this static if here, because I have template constraints here. So if I take my if statement here, I can basically paste it in here. Let me do this in 2 steps here, as a template constraint. Okay, and remember we talked about these in a previous episode. You could search for template constraints here. So now what I've done here, and let's go ahead and line this code up so you have a chance to read it, is I say, don't even get to this function, check the operation here as a constraint here. So, I can only do addition and subtraction with my vectors. Okay, so that's kind of cool here, right? So if I'm working with a vector, I can just do a constraint here. So let's go ahead and try this now. And let's see. Oh, what did I get here? My result. Sorry, let's make sure things are all within scope of each other. There we go. Okay, I think that looks almost correct. There we go. Okay, so this works now. As we intend, we can only do addition and subtraction with vectors. And then it's going to give us the error, operator times is not defined for this, right? It doesn't meet this constraint, which is a little bit better of the documentation. We're saying specifically this isn't allowed. Static if is kind of telling us, what code to generate, which we were using in that block, which was nice. But this is an actual constraint on like what's legal. This is more of a contract, okay? So I like this. In C++, we call these concepts, again, which sort of restrict or properly sort of enforces, something about the semantics of what some function's allowed to do, okay? And that kind of makes sense if we're working with some mathematical type, right? So we don't want to forget this stuff here. But now we've written this function. But we still got to do something about the times operator here. And I can't multiply 2 vectors, but I can multiply a vector, my unit test, by a scalar here, s. Let's make it 7, for instance. So I could do v1 times s here, and write out the result. So let's try to compile, and I'm going to get an incompatible type here for multiplying a vector and a float because, well, I need to write this binary operation here. Okay, so let's go ahead and do that. This time we're just going to take in a float as the type here, s, and maybe I can do things like division, scalar division, and multiplication here. Okay, and then I'm going to rewrite my mix in here. Instead of doing the right-hand side, it's just going to divide or multiply by s. And now I can compile and run this, and it's working, right? 5 times 7 is 35. 6 times 2, apologies, 6 times 7, because that's what we're doing down here, is 42. Okay, so that's working now, and hopefully you can see op binary, again, operating on different types here. Okay, so that's the basics here. There's some other stuff that you can do that's kind of neat. Again, you'll see this in the library code. So for instance, you might just see type of this here for the return type. Sometimes I do that. That'll do the same thing, but again, it'll figure out that this is a vec here. So if you have like a if you template this type, that's just another note here. So for instance, we might have a vector 2 of integers, a vector 2 of floats, a vector 2 we want with doubles. So again, returning the type of this is kind of, again, a more generic way to work with these here. So let's do that just so you can see it'll be something new that's not in the documentation for op binary, right? You'll just usually have a type here. But again, that's something you'll see maybe in other people's code. Okay, so great. We got this far. We sort of remember template constraints, string mix-ins, a whole bunch of stuff, again, as mentioned in this episode, and unit test here. But we're not quite done. I want to go ahead and show a few other things here with operator overloading. And let's write a new unit test here. Let's just see if I want to, let's see some of the common ones here, like op index. That's one that you're probably going to look for. You say, hey, I want the index of this vec2. And this looks kind of funky. I mean, it looks kind of scary. That's why I'm choosing this example here. And this example is showing, in particular, like a multi-dimensional array here. Okay, that's kind of fun. Let's see here if there are some more examples here. I mean, these are some simpler ones. Okay, and we'll do slicing. We'll get to op index. Let's do op index first here. But again, I just want to look at some data structure. Now, what does it mean to index into v2 here? Okay, so let's go ahead and start from the top. Again, op index. What do I want here? Well, this is a one-dimensional thing here, so it's just taking the index. And what am I returning? You know, if I wanted the 0th index or the first index of this, just a float. Okay. So for instance, I could say if index, and again, there's no template here, so I'm just going to say that's why there's no static if, no mix-ins, nothing fancy like that. Then I'll just return x. If index equals 1, then I just want to return y. Okay, so let's just do that here. Let's see if this compiles. Oh, it says, okay, no return expression or assert at the end here. So basically, you know, I've only got two indices here, 0 and 1, the 0th and first element, so to speak here. So I should probably just put an assert here that says out of bounds, you know, or something like that. So that's kind of a nice thing in D. You could either put an assert to say like, hey, you messed up and the control flow should never get here, right? It should always hit one of these two conditions. So you could sort of do that here. Otherwise, again, you can, I guess you could, again, this is just the form if we look at op index here, right? There's no like template or anything. It's just rewriting it as a function call here. So anyways, let's test this out. That should be enough here. Let's see here. I copied this one here. So let's just have v1 here. Let's just have our result here. I'm just going to do auto here, v1 at 0. Well, let's just write this out here. Right? We should be able to say v1 at 0. And I'll put a little colon here, comma, v1 at 0. And let's also do at 1. All right, so let's see. We should get 5 and 6 back here from our test, and we do. Okay, so we're successfully indexing into this data structure, which is nice. Okay, so that's op index. I tend to like, especially if I have a data structure like this, a vec2, to do something. It's a little bit clever. I don't know if it's so clever, but it's just a different way to access this data. And again, if you haven't seen my video on unions, sometimes I wrap these in unions and a struct here. Okay, so an anonymous struct here. So you'll see this isn't going to change anything with our members. It still works here. But what I'll do sometimes is just say, hey, let's have a float of 2 elements here, right? Because I've got 2 floats here. So what's the difference in my union if I access them as 2 floats? So that's just a little trick that I like to do here sometimes. And then it makes my overloads sometimes a lot cleaner, right? Because what do I need to do here? I just need to return e at index here. And then maybe do like a, assert here. Index is equal to 0 or index equal to 1, out of, out of bounds otherwise, right? We would say. Okay, so that's kind of doing the same thing here. But again, we're accessing the same memory, and that's what a union allows us to do, same bytes here. Now, you might have to be careful with like padding and some of these different things here, but again, these are going to be sort of tightly packed. In D, again, we know exactly that a float is 4 bytes. So again, these are some of the nice things in the language. So that's a little bit of an advanced trick, but it might make your, some of these operations nicer to work with. Or if you literally just want to access, v1.e at 0 for some type, right? You can just do that too. So you get all the indexing for free. But again, I tend to like this. The other trick that you can use is with alias this to sort of alias this type as something like this if you don't want to use this union trick, but again, that's more interesting D stuff. Okay, so let's do assignment now. So let's go ahead and copy this unit test and do something else here. Let's go to the bottom here. And let's say that I want to do v1 at 0 equals 55. And v1 at 1 equals 66. Okay, so let's see in our example. Does that work? Oops. Cannot modify the expression because it's not an L value. Okay, so we're not allowed to do this quite yet because op index is just looking at the value, but what if I want to modify it? Okay, we have separate operations for that, because maybe you don't want to be able to modify that, but those are going to be of the form op index assign. Okay, so let's try to find the first one here, and it's just going to be of the form this. This is the form here. So op index, the value that you're assigning to, and then the dimension. We only have one dimension, so there could be two. This is giving you an example of accessing in like a multi-dimension, maybe of a matrix or something. But let's use op index assign. And again, there's no like, let's see, there's no weird like template magic here. I just see the operations here. So I'm going to do, well, let's start with void op index assign here. We'll talk about the return type. The value, which is a float, that's what I'm going to assign to because I have floating point types here. And the index again. Okay, index. Let's make sure we get the types right. Should be a size t because it needs to be a positive value. So no problem there. And again, all we need to do here is e at index equals value. Okay, so simple enough. We do the assignment. Let's see here. Did this do the assignment? Our code didn't crash and it did the assignment. Cool. So that seems to work. Simple enough here. Now, if we look carefully, though, at the D language documentation, it returns an integer in this example. I'll say, well, if I look at this expression, where is it returning that to? So, that could be a sort of design decision of how you make this, or you could have, two versions of this function here. I'm going to go ahead and just say, let's make this a float here. We'll do the assignment and then return the value. So let's return value, whatever is passed in. Does this still work? Let's compile it below. Yeah, I get the same thing here. So that's interesting. Now, why would I want that? Well, let's make this unit test a little bit more complicated. Let's say I do something weird like this. Auto float equals this here. Well, let's make a separate unit test for it because it's kind of a separate case. But we're going to make it a little bit more complicated. And, well, I mean, let's just say I want to wrap this in an expression here. Okay. So in a parentheses. And let's do it in the right line here, actually. Let's say, let's do v1 of 0 equals 55. And I'm going to wrap it in parentheses here. And let's do v1 equals 66. Okay. So do folks see the difference here? This is just doing my op index operation here. This is doing my op index assign, but then it's going to return a value here in right line. Now, if I'm returning void here, this isn't going to work. Okay, so this works just fine. But if I go back to my example where we had like this void, let's see if this works here. Now it's going to complain because right line's just seeing void here. Okay, there's no return value, so it's like, hey, what am I putting here? So that's why, it might be worth just returning a float in this case here for your index. And of course, you should probably have your assert. Okay, try to make this a little bit more production grade. Okay, so great. So just a little reminder there on how some of those things work. And we got a little bonus review on unions here. Okay, so the last one that I'm going to do here, I mean, again, there's a ton. You could do op index assign, and I probably want to do slices just because I think that's the least likely one there would be examples for. So let's do op slice. I'm just going to put a parenthesis here to try to get me to the first example. And this is interesting, where you can see we have a bunch of examples here. Let's try to find the spec here. This is for like op index assign. So assigning a slice. Ooh, you can assign a slice to some value here. That's cool. Let's just do we'll do a little bit more of a basic one. let's just work with a slice to retrieve like the values here. And this is nice because we have the built-in arrays, which we know how to work with slices, but how do we get this to work here? Okay, so for this, let's again start with op slice where we want to work here. Let's create a new unit test for our slices. And basically what I want to do here is do something like auto my slice equals v of 0 to 1. And let's do my slice 2 equals 0 to 2 here. Okay. And we'll write these out here. My slice 1 my slice 1. Okay. And let's go ahead and set this up here. And let's go ahead and try to compile this. Okay, let's see what happens. Oops. Sorry, there we go. Okay, so does slicing work? Oh, we got some errors here. We got to make our v1 here. And let's make sure we compile our vector. Okay, so let's just set things up before we get to slicing. Okay, so no operator overload for this type here, so we can't do this operation here. Okay, so that's a problem. We got to figure out how to do that, and that's what we're going to implement here. So let's start with our op slice, and we'll kind of have to study this. Okay, the dimensions. This is a two-parter. Okay, to overload array slicing of the form a of whatever our slice, 2 steps are needed. First, the expression of the form I ... j are translated to op slice for 0 dimensions here. So again, we don't have multiple dimensions, into objects that encapsulate the endpoints I and j. Then these objects are passed to op index to perform the actual slicing. Okay, so two-parter. So it looks like I need this guy and this guy here. Okay, it's giving me the minimum viable product here, minimum example. Okay, so let's copy this signature here. So I do have the dimensions here, which is kind of interesting. An I to j. Okay, so that's going to be what I'm slicing through. And then this is kind of interesting. Okay, this one's just looking at integers. We're going to look at floats here. Okay, on the left-hand side of our screen here. So we probably want our slice to be of floats. Okay, so let's try this out here. So size t, dimensions 0. Okay, and then what did we have? I and j here, and then get positive values. So size ti, size tj. Okay, and what are we returning in our slice? Float array of some sort here. Okay. Okay, and that's just going to be e from I to j here. Let's see if that's enough, because we do have op index defined here, right? Oh, there's a different one here. There's like an array thing here. So I mean, let's see what happens. If I compile it, okay, still not callable here. It says we need this candidate that we have, but it's not callable. We need to define this guy here, op index, and it's going to take in whatever the slice type is and then return it. So let's kind of look at that here. So again, these were going to be floats, right? Float, op index, float, the slice, and then return our slice here. Okay, does this work? Let's compile it. It does work. Okay, now let's try to understand why, right? We shouldn't be too surprised. So vec with 5 and 6, that's 2 values. If I want the 0 to the first, 1 not included, that just gives me the first index. And if I want 0 to 2, that gives me 5 and 6. Okay? And again, this could be very handy for a vector type of operation, but let's try to make sense of what's going on here. So if we look at in D how it's rewritten, right, I have the brackets here. Okay, that's the first thing here. So anytime I see brackets, I'm thinking about indexing. Okay, so that's the first thing. So I'm indexing, I have brackets. So when I have brackets, that means, okay, I need some, what am I indexing into? Well, some type of floating point array here. Okay, so that's why I have float on the op index, right? So folks understand that my vector consists of an array of floats, or at least that's what I'm trying to get out here for this particular part of the data structure. And then I return that slice. Okay, so if I return this slice here, and the input is, okay, the input's this guy here. It's rewriting it, or the compiler understands op slice 0 to 2, the dimensions here. Well, this is the inner part of this. This is returning this float part here. So, I mean, ultimately, all I'm really doing is kind of hijacking, D knows how to use this portion here. Okay. So it says, okay, I want to slice 0 to 1, working my way inside to out, 0 to 1 in this particular example. That's the op slice part, the dot syntax here for op slice. And I've only got one dimension, right? If I had more, right, if it's all syntax that looked at the form like this, right, that dimension value would change. So just kind of working inside to out. Oops, sorry, let me go back to a unit test. So again, that's why the op slice part, that's this guy that it's doing the translation for. And then again, I see brackets, so that's op index, okay, because I see the brackets, right? And what's this guy returning? Op slice? Oh, float array, which is what op index is taking. That's my slice. And that's this guy here, right? Which, I have the overload already for a basic primitive type here. Okay, so hopefully that helps make a little bit of sense. That's probably one of the more complicated ones. I guess you could look at op slice assign with multiple dimensions. That'd be a good challenge for you in this lesson. So if you weren't already having fun, try that one out here. But it's relatively clean. It's well defined, and it's really cool that in the language you can, have slices for your data type. I do this with my like vec2, vec3 matrix types. It just makes them really, really nice and easy to use. And again, that's sort of the point here when we talked about the how and the why, and the whole purpose of operator overloading here is that if you have some math type, right, it's really convenient for us to do something like, let's write a unit test here. And again, okay, all of my vectors are going to be at the same dimension here, but I could take a slice here, and then, well, I might need to do a little bit of work here, but let's see if this works here. I mean, this would be the idea here, that I would be able to do something like this here. Let's get rid of my slice too. Now, these are going to be floating point values, so I don't know if I know how to do plus on those. I wonder, I can't cast them. I could try to cast them, right? You could try to force the cast here. But this would be the idea that you could say, well, I just have two floating point values, force the cast, and then you know how to do the plus operation and then write it out, etc. But so again, we have, sorry, I've got to do one more opcast, right? We'd have to overload that to say, okay, can I take a float, two floats? What does that mean here? Some float size, and then I could cast it to a vec2, and then I could use the plus operator. So, I mean, my point is this stuff's just very, very flexible. You have all the power that you want. So you could take a slice of a data structure. Maybe if you had a vec3, take a slice of the first two values, then it's a vec2, and then do something with it. So anyways, those would be the things that you build into your library here. Yeah, let me get rid of this otherwise. But it's all there. It's all in the language so that you could do this stuff here. And it tends to work well with math types. If I have some other functions or operations that I want to do on a vec2, the type of the things that I'm not going to do, for instance, in this particular case is I'm not going to overload times to be like cross product or dot. Right? If I have other functions, I am just going to do like for like dot, or let's call it inner product or scalar product or something, vec2 v1, vec2 v2, and then I would return v1x times v2.x plus v1.y plus v2.y. Okay, so my free functions, my other operations, are things I'm just going to define outside here that might use vec2s. But I'm not going to overload symbols for that. So again, there is sort of a difference here of when to use it. So again, pure like plus minus operations, I tend to use stuff for. Other things like inner product, or probably just called like dot, or depending on your style, dot like that, I am going to just define as free functions. So I don't use those things as overloads. So anyways, I'm just going to point you briefly, because this video is getting long. It's been packed with interesting stuff in review about like why it's different from C++. Again, one of the big advantages is there's only one place to put these operator overloads. It's within the actual struct or the class that you're using. You don't have these just like freely hanging around. You write the free functions instead, like dot, for instance. So again, that talks a little bit about that. And not having, all these other like random symbols is kind of nice. And changing the operator precedence, right? You don't get surprised by things that are happening. And again, yeah, so it's just kind of nicely done. There's a little bit of the rationale I'd encourage you to read here. But that's it. We did a lot of review here. I'm going to scroll through the code once slowly in case you just want to get a view of it here. Starting from the top, our vec2 data structure. We'll page down a little bit. Some of the things that we did with op binary, op index assign, and we discussed using mixins, strings, why we return the results, using sometimes type of this if our type vec2, for instance, is templated. That can be handy. Why we write free functions and don't just have like op binary freestanding everywhere. That's just as good for the type, and we can template this again and do the proper thing if we need. And then don't forget about your unit test. If you're doing operator overloading, unit tests are a great tool to use. So there you have it, folks. That's probably one of our longer videos, but we reviewed a lot of stuff, so maybe I'll title this like review and introduction of binary. But if you've watched the videos in succession up to this point, you're in a good place. Or if you've done some deprogramming before, hopefully this is familiar stuff. But again, it's kind of pushing you towards developing a library. So I had a lot of fun doing this. I hope you had a lot of fun watching this, and as always, I'll look forward to your comments in the discussions, and I'll look forward to seeing you in the next one.